Hey students, all right, I thought I'd make you a video solution here for exam number 2. Again, like before, take a moment to go through this and you can both self-correct so you got a rough idea of what your grade is, as well as find your mistakes so that you can learn from those mistakes. And that being said, you might notice by the color of the table here, and also kind of the shadows. I'm not in my normal setting, so I hope the lighting's gonna come out well on this. I see I got a bunch of shadows here, but it's the best lighting I could come up with. All right, so let's quickly go through these 10 multiple choice ones here. The first one, it looks like it's right out of chapter 6 and our circular motion. It says, when a car goes around a banked curve, the bank curve is engineered to complete the turn without the need for friction between the tires and the road. All right, so if you do kind of a side profile here would be the incline. Here would be like the front or the back of the car. And so you got to kind of visualize this in 3 dimensions, and it's kind of curving around here. And so this is angled at some angle, which as we keep reading will be 45 degrees. The need for friction between the tires and the road. Suppose that the curve has a radius of 20 meters. So that means, again, if you're thinking in 3 dimensions, as the car goes around, this right here is the 20 meters, and this is the center of the circle. And we've got it banked at 45 degrees from the horizontal. And then, of course, what is the speed of engineering? And so if we do what we've been calling the free body diagram here, and so I'll just kind of draw the car and say, okay, what forces are on this car? Well, clearly there is the mg, and of course then the road is supplying what we call a normal force. However, the friction can be ignored between the tires and the road, because we're going to design this so, again, you don't need any kind of friction to make this turn. And so this could be a tough problem, although we've done a lot like this, so I'm hoping you didn't have much difficulty on the exam. But one of the things that I always emphasized, and maybe I didn't give myself enough room here, so let me go ahead and see if I can find a scratch paper here, all right, and bring this onto the screen, is that divide your paper into 2 and do your forces in the x direction and also in the y direction. So in the x direction, if you come back to our free body diagram, we need to pick a grid. And I think the best grid, as you've heard me say, is to set up a grid so that one of your axes is towards the center of the circle. Because we know that if something goes in a circle, it has a net force of mv squared over r, or maybe I should say an acceleration of v squared over r, and it's towards the center of the circle. And so if we set that up, and so I'll call this kind of the x direction and this the y direction, we know then that when we add up all the forces in the x direction, we're supposed to get mass times acceleration in the x direction. And in this case, it would be mv squared over r being the radius. And that was the nice thing about setting the x-axis to be towards the center of the circle, because then the acceleration in the x direction is v squared over r. And it also is kind of nice because the sum of the forces in the y direction, which equal mass times acceleration in the y direction, would be 0, because we set up the acceleration, in the x direction, and so all the acceleration is in the x direction and nothing is in the y direction. And so that's a big part of this problem. Then, and I've kind of got away from my free body diagram, when we look at this, we can see that this is tilted by this angle of 45 degrees, and then the only thing in the x direction is the opposite component of this 45 degrees. So when we add up the x direction, we're going to say n, and we're going to say sine of 45 degrees. And that's it. That's all the x direction that there is. And so I'll set this equal to mv squared over r. And then over here in the y direction, there's more forces. And coming back to the free body diagram here, the upward or y direction of this would be n cosine theta. So I'll write that here, n cosine of 45. And then another y component is gravity, which is just mg, and it's the full force of gravity. So that's kind of nice. So this would be then minus mg equals 0. And then, of course, we now have these two equations we can manipulate. I'll start here with the y direction and say this is mg divided by cosine of 45 degrees. And then I will put that over here in the x direction. So this is mg over cosine of 45 degrees for the n. And, oops. And then we have the sine of 45 degrees. And then we got the mv squared over r. And then the m's cancel off. And one of the things that might bother you, and it always does when I first read this, is they don't give the weight or the mass of the car. And then fortunately, as you'll see, we don't need it here for this question. And now as I manipulate things around, I'll bring the r over to the left-hand side. I've got g. I'll put the sine and cosine together for a tangent, and then I'll have my v squared. And even to make it easier, the tangent of 45 is just 1, and so the r is 20, and then we have the 9.8, and that's equal to the v squared. So here we're going to need a calculator, and here's where I'm going to need to borrow one here. And so I'm going to borrow a phone here and say, all right, so this would be 20 times 9.8, and then, oh, that's a perfect square root. I guess I didn't need a calculator for that, but I'll try it, and that should be an even 14. So the velocity should be 14. Okay, so with that in mind, then I'll go ahead and say, all right, the answer would be C for number 1. All right, well, that was a tough one to begin with. Let's try number 2 here. Here it says, a new satellite is designed to study the climate and is placed in a high orbit 1.5 million meters above the Earth's surface. Again, what is the speed of the satellite? So again, this chapter, which involves circular motion and gravity, are kind of put together. As we just did in number 1, we know that the acceleration would have to be v squared over r if it's going in a circle. And so if we add up all the forces, that has to be equal to ma, which is mv squared over r. And in this case, if we're talking about just the planet Earth and we've got a satellite orbiting around, the only force is the force of gravity. And so when I say you add up all the forces and set it equal to mv squared over r, again, very similar like we did in number 1, except number 1 we had 2 different forces. We had a normal force and a weight force. Unfortunately, we didn't have any friction. That would have made it that much harder. But what we would have here is only one force, and that's the force of gravity. And so this is the universal gravitational law. And that is the G, capital G, mass of the Earth, mass of the satellite, and the radius squared. So if I set that to the mass of the object orbiting, which is the satellite, and v squared over r, I've got a problem that's a little bit like the first one, but also has its differences. And in this case, then, we get v squared equals to g, mass of the Earth, divided by the radius, okay? And this one can be a little bit hard because down here, the radius of the orbit would include the radius of the Earth plus the altitude of the satellite. So if we look here in the book, the radius of the Earth is 6.37 million meters. And then the problem says we're going to place it above the surface here in a high orbit, 1.5 million meters. So this is going to be 1.5 million meters. And so together, when we add these two, that's a 7.87 million meters. And then the g is the 6.67 times 10 to the negative 11. And the mass of the Earth is that 5.98 times 10 to the 24 that you've seen quite a bit. And then we're just going to have to take the square root. All right, so let me do this on this older style calculator. Let's see, where is EE? There it is. So if I go 6.67 EE negative 11. Okay, that looks good. And then times 5.98 EE 24 equals. Then if I divide it by 7.87 EE6, enter. That should be the velocity squared. And so taking the square root of that for a final velocity of 7, and I guess it'd be 120 meters per second squared for my significant figures. So with that option, it looks like we are looking at A here for number 2. All right. Again, another long one. Hopefully all of them aren't quite that long. Let's look at number 3 here. Number 3 says, in 2 seconds, a man lifts a 20 kilogram mass or weight or something, 20 kilograms to a height of 1 meter above the initial position of the mass. The mass is originally at rest, but upon reaching a height of 1 meter, it has a velocity of 2 meters per second upward. What is the power? And so if you remember, power is the rate at which energy is being done. And so in this case, we've added energy by giving it a height, and so that's gravitational potential energy, but we've also given it some kinetic energy. And so this should be 20 times 9.8 and a height of 1. And this one should be 1/2 times 20 times a speed of 2 squared. And the time is 2 seconds. This one looks easy to do because this is 10 times 4. So we get 40 joules from its kinetic energy. And this then would be, I guess, 19.6 over 2 seconds. And then if I add these together, let's see, that's a 6 and a 13, carry 1. That's a 236 joules in 2 seconds. And so Half of that's 100, 15, and 3 is 118. And that would be joules per second, so that would be watts. So it should be answer C for number 3. Okay. And kind of avoiding using a calculator, so see how that works. All right, so number 4 here says, a body of mass capital M is traveling along the positive x-axis at a speed of v, but then it explodes into 2 pieces, each with a mass of 1/2. One piece is still traveling along in the positive x direction, and the other is now going to travel in the opposite, that is in the negative x direction. Which of these speed options listed below is possible, of course, into the law of physics? Now, that was a vague way of saying momentum, because that's the thing we know is that momentum would be conserved here. Okay, so if I look at before the explosion, we would have a mass m traveling with v. So there's no hard numbers here, and that can make it a harder problem because we're going to use symbols. And then after, I guess we're going to have a half a mass, and I'll call the speed in the negative direction. And then we'll have a half a mass times the speed in the positive direction. And that, of course, has to be the same as before the mv. That's the principle of conservation of momentum. Remember, momentum is conserved as long as there's no outside forces. And so if you think of kind of my 2 fists here as being the 2 pieces, they come along and they go, well, maybe I'll start out of the screen, and they come into the screen and they go boom, and one goes left and one goes right. But there is not an external force. There is an explosion within themselves, and that adds energy to it. So that's why we couldn't use conservation of energy here. But we must use conservation of momentum. And so if we kind of look at these, you can see that 0 speed for each would not work. And also a speed of v for each one would not work. If I put a v here, although we must remember this needs to be inputted as a negative v because it's going in the negative direction. That's another little subtlety here. But if I put a v here and a v here with the negative, that comes out to be 0. And likewise, for half speed, it still comes out to be 0. So those don't work. Hopefully this last one will, and I think it does. You can see it here. If I put the mass m/2 with a speed of negative v/2 for the one going in the negative direction, and then add that to this one, which has a mass of m/2 and a speed of mv/2, you'll see that this right here is a negative 1/4 mv, and this one here is a plus 5/4 mv. And if you have a plus 5/2 and minus 1/4, that's 4/4 mv, which is just mv. And so yes, that one would end up with the same amount of momentum. So number 4 would be D, and that could be a tricky one too. In fact, I guess we're getting to harder material, and all these can be trickier, much harder than the first exam. All right, so on to question number 5 here. It says we have a 3 kilogram, 1.4 meter long rod that's free to rotate around one end, which is labeled as A. And so maybe I'll put a little mark here and say, okay, this rod can pivot on down. And it's in the horizontal position when it is released from rest. At the moment it is released, okay, so not swung down here as kind of shown with this dotted line, which is eventually going to happen, and that's the next problem. But right here, what is the angular acceleration? And so if you remember Newton's second law, F equals ma, add up all the forces, we have now the harder mechanics problems of things that rotate. And so this would be Newton's second law due to rotation. And so we've got to add up all the torques. And so if you do a free body diagram here, you would have gravity pulling down at its center of mass. And that's important. Now, that's what makes this rotational mechanics much harder than everything else, than what we've been doing, because we have to think about its position of the force. And I guess likewise, there is an upward force at the hinge. But when it comes to doing torques, since torque is the distance away from the pivot times the force, the torque we get from this one would be 0. And the torque we get from this one would be a distance of half the length of it. And so that's important. We can't just use the length of it. We got to use half the length. And then mg. So there is the sum of all the torque. So I'll put a L over 2 mg. Okay, and then again, being a rotational problem, we need to know the moment of inertia, which is more complicated than just the inertia. And so looking at that table, and I guess chapter, I believe it's 10, we'll see this labeled as 1/3 the mass of the rod times the length squared of the rod. And then the unknown we're trying to find is the alpha. And then fortunately the masses go away, or maybe we're not needed, because this problem, if anything makes it an easier problem, is the fact that we can actually put in the L, the M, and the G and get a number here, and we can put in the M and the L and get a number there, and then just solve for alpha. But we could also simplify it, and we won't even need the mass. And for that matter, one of the L's would cancel. And so when we bring the 3 over, we get 3 over 2. We get a G over an L when we bring the L downstairs, and there's our angular acceleration. So again, a rotational problem. And like I said, the torques are just harder because they involve position and the position of the center of mass when it comes to weight. And then the moment of inertia is harder because it involves distances. And so just Newton's second law of rotation is just harder than what we saw in the last test with Newton's second law of translational motion. Anyways, getting my calculator back here. All right, let me bring the calculator back into the screen here. Let's see, 3 over 2, I'm going to put that as 1.5 times 9.8. Then divide by the length, which is 1.4, and hit equal. And it looks like I've got about a 10.5, and the units would be radians per second. And it looks like C would be the correct answer for 5. Now keep all this in mind because number 6 has the same basic setup, but I think it's going to involve, instead of forces, energy here. Let's see. Yeah, like the previous problem, so same mass, same length, the free is rotated around A, so I'll just do a little mark there. And it starts off in its horizontal position and at rest, and after a small moment in time, the rod drops and is now in the vertical position. So they're talking about it swinging down to the vertical position, and they're asking then for the angular speed. And so my hint to you was anything that involves, say, time or forces, or in this case torques because we're rotating, use Newton's second law. And so they asked for acceleration, and hence I quickly went to Newton's second law in number 5. But in number 6, if they're asking for speed and they're giving you the position, and in this case angular position, but if we just drop the ball straight down, I would say it's vertical position, those are clues about using energy. And so that's why this one I'm going to approach with conservation of energy. And I'm going to say the initial energy equals the final energy. Now, here's where it gets kind of interesting, and we have a decision to make here. Because energy, and particularly the potential energy, MGH, H is measured from some reference point, wherever you want to call 0. All right, so where do you want to call 0? Usually, mathematically, it works out best to call 0 the lowest point, and that way we don't have any negative heights, and one of them probably comes out to be 0. But I just kind of have a gut feeling that many of you might call the lower edge of the swing 0. And that's maybe the lowest point of the rod, but remember, we need to be thinking now of center of mass. And so just like the last problem in number 5 here, where we said, okay, what is the center of mass? That's where the torque is acting. Again, that magical point, that center of mass, is where all the mass would be. And so it actually has the lowest point right here. And so the problem would be a little bit easier if I called this 0, but I'm not going to. I'm gonna do this just because I think a lot of you guys will. And I'll just add one extra term. So let me do that, because what that would mean is when it comes to initial energy, I would have an mg, and this would go up the length of the rod, okay? And so that's the gravitational potential energy. And just for completeness, let me put a 0 because there's no kinetic energy in this problem to start with. But then as it swings down and it gets to this position, it is going to have a kinetic energy. And it's a kinetic energy of rotation. And so it's a 1/2 I omega squared, not a 1/2 mv squared. It's not translational. And then, because I called this 0 and it swung down, you can see that the object still has a height of L/2, which you will notice mathematically, when I bring it over here, I get an mg L/2 equals 1/2 I omega squared, which is what you would have gotten straight away had you called this position 0, because you would have said the starting height is only L/2 and the ending height is 0. And so, of course, not a surprise, which is why we said you can pick the height of 0 anywhere you want. You just got to stick through it for the rest of the problem. All right. So whether or not you did it my way or maybe a little faster way, or you could, by the way, have called this height 0, and so then it finishes at a negative L/2, but started at 0, and then you move that over, changing the negative to a positive, and you still end up with the same equation. So you can see that it doesn't matter where you call the height equals to 0, as it, rightfully shouldn't matter. Well, like the last problem, a rod rotating around its end point has a moment of inertia of 1/3 ml squared. That was, again, in the textbook there, chapter 10, table 2, I believe it was. So I'll put that in, and then I'll put the omega squared. I'll put the mg L/2. And again, like the last problem, we could just put these in and get numbers, but we could also maybe save a little bit of work and cancel the m's. We don't really need the m's. We could even cancel a 1/2 on each side. That's kind of nice. We could even cancel an L on each side. That's kind of nice. So I'm just left with a G on the left-hand side of the equation. And it looks like I still have the 1/3, which I'll bring the 3 to the other side. So that'll bring it upstairs. And I still have an L, and then that's going to give me my omega squared. Okay, now, let me see if I can grab my calculator here again. Let's see, I need to unlock it here. Here we go. Okay, so using this phone for my calculator, I have 3 times 9.8, and then divide it by the L, which was the 1.4. And so that's omega squared. So let me take the square root of that. So we're looking at about a 4.58 radians per second, which would be option C here for question 5. Okay, good. All right, well, moving right along here. Here is a tricky one, or maybe I shouldn't say tricky, hard one, because again, it has to do with rotation. And so if you had a grid and you put M at these locations, and so we are at negative D 0, and 0, negative D, and so D away. Another one at D 0, and another one here at 0D. And we learned that the moment of inertia is M times its position away from the rotational axis, which would be a distance of D. So this should be the moment of inertia now of one of them. So let me do that for all 4 of them, and I would have an MD squared. And so that would be answer D there for question number 7. But again, it's that rotational mechanics that can be hard. In number 8 here, it says in some mechanical operations, a disc or a flywheel, again, more of the harder mechanics, is spun to store kinetic energy. Now, let me just write down 1/2 I omega squared. This is the kinetic energy that we used back here in, I guess this was question 6. And so we're going to be looking at energy here. But it's a good way to store energy. And in this case, they give us the radius, and they give us the mass, they give us its speed in radians per second. We will need to either remember or go look up the moment of inertia of a disk. And so this is where this problem becomes a little different than this one, because this is a rod about its edge. And this then is a disk around its center. And so looking in that table, we see the 1/2 mr squared and then the omega squared. So this 1/2 and 1/2 make a quarter. Looks like the mass is a 20. The radius is 0.5 squared. And then we've got 100 squared. Well, that would be 20 over 16 times 10,000. I guess this reduces to 5 over 4. 4 goes into 10,000, 2,500 times. And so we're looking at a 1250, right? So that should be answer B here. Nice. And I did everything in the base unit, so the energy would be in joules, but all of our energy options are joules. In fact, the whole test, it's not like the first test in chapter 1 where we had some issues with energy. The units aren't really being tested here. It's more about the mechanics here. All right. Well, finally, actually, we get into our fluids. And if you remember, this is the first chapter on fluids, and as far as we got here before the exam. But number 9 says we have a diver finds that the pressure at a certain depth is 10 kilopascals. Now, maybe I should remember then that the unit here is a kilo, so that's 10,000 pascals, which is 10,000 newtons per square meter. I say all that because we know pressure is force over area, or rewriting this, the total force on something is the pressure times the area. That's why, things like a car tire, you have 4 of them, and they actually touch the road on quite a bit of area, so you don't need much pressure in order to hold up the full weight of the car. And so, car pressures, you don't have much. You have like 35 psi. But a bike tire, you'll have like 100, kind of a road bike, because there's just such little area, and to hold just the weight of a 200-pound person, you're going to need, maybe 100 psi in order to ride the bike. So pressure and area together. Anyways, so this is this idea that if you were to take a sample jar, underwater, there could be a lot of force on it, and it might damage your lid or rupture it or something. And so you got to, maybe do a quick calculation. So I need to know the pressure and the area is in square meters, and the answers are all in newtons. So that's my clue to say I want pressure in pascals. So I'm going to change that to 10,000 newtons per square meter, so that when I multiply it by 0.04 meters squared, let's see, that would be 2 decimals here, and then times a 4, so that would be 400. And so that should be answer D for number 9. Okay, well then the last of our multiple choice before we move on to the free response here is a conceptual one, but actually a pretty challenging one here, because it says salt water is slightly more dense than fresh water. Okay, so when you have a 50-ton ship, will experience the greater Bay force in which? Freshwater, salt water, or will they be the same, or can you not determine that from the information given? And here's what we do know about a floating object. If this is, say, the water line, let's go ahead and put our object in here. And I'll make kind of a boring looking boat here. But what's going to happen is, because the boat floats, it, displaces a volume of water that's less than the full volume of the boat. But in my free body diagram, what's being pulled down is mg, and what's lifting up is the buoyant force. And then this just goes back to our basic translational motion, or sum of the forces equal ma. We want it to float. We want it, to not be sinking down in the water or being pushed up. And so the acceleration is going to be 0. So these two forces must balance. That is, we must have a buoyant force equal to the weight of the boat. And so if the boat weighs 50 tons, well, then the amount of water it displaces is 50 tons. Now notice so far I haven't said anything about fresh water or salt water. There is something that's different, but not related to this question. If what I've drawn for you happens to be fresh water, then we draw another picture in salt water. The logic is still the same. That is, what's pulling down, mg, has to equal what's lifting up, which is the buoyant force. However, according to Archimedes' principle, the buoyant force is equal to the weight of the water displaced. And since salt water has a greater density, to get that same 50 tons, we don't have to displace as much volume. And that's the key here, It's that, hey, both of these are going to have the same buoyant force. They're not going to have the same volume because salt water is more dense. But this question is not asking about the volume of the water displaced. It's asking about the buoyant force needed. And so C would be the correct answer there. So that's why this one can be conceptually hard if you're mentally thinking about volume when the question is asking about forces. All right, well, there's the multiple choice. Let's move on to the free response. Let me get my pad of paper back here. I guess I'll get rid of this piece of paper that we needed for one of the problems. Let me start with 11A here, and maybe I'll read it here first. But it says here, two coasting spaceships, one with a mass of, and the other with a mass of, are traveling with a velocity that are perpendicular to each other. The bigger one is traveling along the x-axis at this speed, and the other one is traveling along with a slightly lower speed in the y direction, and they collide and stick together. All right, so in my picture here, I guess I have the heavier one, the 2,080 kilograms, traveling at 30.5 meters per second in the x direction. And the lighter one, the 1,250 kilograms, is traveling with a speed of 25 meters per second. Okay? And then they're going to hit. And in my case, I'll just make their contact point the origin. And then they stick together. And hopefully, conceptually, you're back to this idea like we did in the very first problem with the two masses exploding. There is an energy interaction, so we can't say that the energy before equals the energy after, unless we include, in this case, energy of heat formation, which is part B of this problem, so we are going to have to think about that. And then problem number one on the test, we had to get the energy of the explosion, and we had no way of doing that. Oh, you know, I said number one. That was not number one. But when the one that was cut in half, oh, there it is, number four. So number four. But we could not do this one by energy. We didn't know enough about the added energy from the explosion. Here, we're going to have a loss of mechanical energy that's going to go to heat, and we can get that by doing the momentum. And what I was getting at here is the key to this problem is about momentum, and what makes this a little bit harder than number four is there's a momentum in the x direction and a momentum in the y direction. And so when we do that, we have to say, okay, the initial momentum in the x direction has to equal the final momentum in the x direction, as well as the initial momentum in the y direction has to equal the final momentum in the y direction. And so I need to do the two of these together. And of course, there is going to be some then angle, because the problem says, if you can see it here, it says they collide and stick together. And so now they're going to be moving off at some, I'll just say some final speed, and I guess I don't know what that is. But when they stick together, it's going to be like one object. So I can just add the masses. So 2,000 and 1,000 is 3,330 kilograms is their total mass. Okay. Now, if anything's nice on this problem, it is that this first one in the x direction has all of its momentum in the x direction. So if I just go 2,080 times 30.5, and then I'll say plus 0. And the zero's there because to get the total momentum, I got to get in the x direction, I got to get the x component of the first one, and it's all of it, and then the x component of the second, which is 0. And so that's kind of nice here. So if I grab my calculator here and go 2080 and multiply it by 30.5, I get 62,400 for the initial momentum in the x direction total. And maybe, should I jump to this column or finish this one? I'll jump over here because the same thought process can go on for the y direction. That is this second one, having a mass of 1,250 and an upward speed of 25. Its y component is all of it, and the y component of this first one is 0. And so by that same logic, 1,250 times 25 gives me 31,250 for the initial y momentum. And of course, what's nice about this, and there's a couple ways we can do this, but I think I'll take the easy way out and avoid the trig until we need it. I can just say that then the other side of these equations would be after the collision, and I'm going to just think of it as a single object that has a mass of 3,330, and so this would be the velocity in the x direction. And this one over here would be 3,330 times the velocity in the y direction. Of course, then this right here would be the final velocity times cosine of whatever this angle is. And this one here would be the final velocity times sine of theta. But see, I don't know theta, so I want to avoid that for right now. Let me just make it a little easier on myself and then just get the x and y components of it. And so, well, since this is already in my calculator, let me do the y one first. I'll go divide by 3330. And so the vertical speed is 9.38. And the horizontal speed, 62,400 divided by 3330. And so this is going to be an 18.7. And so there's my two different speeds. Let's see. Did I hit that right? 080 times 30.5. Yeah, I thought it was a little bigger than that when I made it. So I must have hit something wrong there. I apologize. I'm glad I kind of remembered setting this up as a little bigger number. Now let me divide that by 3330. Yeah, that's what I remember. Okay, 19.05. But now I really wish I had the calculator where I can go back and see what I did before. I missed my TI-84. I guess we get spoiled these days. I guess I'm just glad I don't have to do all these calculations by hand, too. Okay, so moving on with this problem, you could now say that, okay, as this thing goes flying off as a solid object here, the object would have a horizontal x speed and a vertical y speed. So if you wanted to know that angle, you could use the trig function tangent, because that would be the vertical speed over the horizontal speed. So that would be the 9.38 over the 19.05. And so we can get the answer to part A, which is what angle does it go off on. All right, let's see. Here's tangent. I bet if I go, yeah, there we go. Inverse tangent. Oh, wait. That's right. It's an old school calculator. So 9.38 divided by 19.05. Okay, so there's the ratio, and I want to take the inverse tangent of that number. So I think if you go inverse tangent of that number, yeah, it just processes it. There's no like equal, so it's more of a function. Anyways, trying to remember how to use the old school calculator. All right, so here is my 26.2, and that would be the answer to A. Now, B is where I'm going to do this conservation of energy. That says, well, the energy you start with equals the energy you end with. Oops, I guess that was off the screen. Let me pull that back up. All right, so 26.2. And so the energy you start with is equal to the energy you end with. And so let me look at the kinetic energy beforehand, the 1/2 mv squared of the first one and a 1/2 mv squared of the second one. And then after they collide, there's a 1/2 mv squared. But then there's also all of the molecules bumping into each other, making heat. And so that's how I'm going to get the heat here. Now I want to be careful in my symbols. This is the first object, and this is the second object, each before the collision. And maybe I will just go final and final over here, because this would be what's going on afterwards. And in fact, why don't I figure out what that speed is, because I do have the x components, and so the x component squared and the y component squared is equal to the total squared. Then that's going to give me a way to get the, oh, that's off the screen, and this is going to give me a way to get that final speed. Okay, so let me take the 19.05 and where's the square on this? Square it. And I better write that down. 36.2.9. And the other speed, 9.38 squared. That's going to be 87.9. And so let me add the 362.9. That's the two together. And let me take square root. So it looks like for final speed, we've got a 21.2. So let me use that right here to get the kinetic energy after the collision, because I already got that number there. Let me go back and square it, and then go times the mass, 3330, and then times the 1/2. And so we're looking here at 750,722 over here, the first object. Clear that. And maybe I'll go with the speed first. If you remember, that first object was going 30.5, and I'll square that. And working backwards, its mass was the bigger one, the 2080, and then the 1/2. And so this right here is the 967 for 60 joules of energy. Whereas the second one, which is just barely here on the screen here, has the 25, which I'll square. And then the mass is the 1,250, and then the 1/2, so I'll just kind of do everything backwards, is the 390,625. And so if I add these two together, plus 967, 460, boy, I missed my good calculator. But that right there then is the total. 1,358,000, I'll just round it. And that's the total. So if I subtract off the 757.22, we are looking somewhere in the area. Probably should have just went to another sheet of paper. It's not going to fit. I thought it would fit here. The heat is about 607, and I'll just do 3 significant figures. So about 607,000 joules of heat energy. And again, hopefully that went well for you. But again, a nice collision, two-dimensional collision. Momentum, both X and Y, and energy. A lot of pieces to it. And hopefully you got it right. And if not, most of it right. How about that? All right. Well, let's look at the second of the free response here. Here it says, suppose that a solid rubber ball with a radius of 10 centimeters is rolling with an initial speed of 4 meters per second along a short horizontal path and then continues up a ramp of an incline of 30 degrees above the horizontal. To what maximum height above the ramp's bottom? Notice it says height. It's going to be interesting because that's going to mean our 30 degrees is going to be kind of unnecessary. Does the ball's, ooh, this is going to be tough, center, and it's underlined, so hopefully you caught that, roll up the ramp before coming to a temporary rest. And notice it says ramp's bottom. So let's watch this for a moment. If I draw a picture of this, and so here's the bottom of the ramp, and then it angles up at 30 degrees. Okay. Now, the ball is here, and this is going to be important and could be very easily overlooked. In fact, if I was guessing, I would say if there's anything that gets overlooked, it might be this right here, because this has a center of mass that is at a height of the radius. And if you remember that conversation we had earlier in the exam on the picking the reference point for our energy, and I guess it was back here on this piece swinging downward, we can pick it anywhere we want and we'll get the same answer. And that's still true. However, as you read the problem, since it says the answer is from the bottom of the ramp, let me use that as a guide to say, let me measure everything from the bottom of the ramp. You don't have to, but you do mentally have to make it very clear to yourself where you're going to measure it from. And so I think the natural place is right here at the bottom of the ramp, because as the ball rolls up the ramp and gets right here, then we can say it has a height of h. And so when we go to calculate its gravitational potential energy, I can measure from the bottom of the ramp. Well, again, this is clearly a problem involving energy because it has to do with position and speed and heights. And so, well, height is position, so I guess that was repetitive. But anyway, it has to do with position and it has to do with speed. So if I do the same thing, initial energy is equal to final energy, I can begin here by saying it has, or does it have, an mg, an initial height. And that depends on where you are going to call your height equals to 0. And again, if you do it from the bottom of the ramp, which I would recommend because ultimately the question is from the bottom of the ramp, that means that this right here has an initial height of h. And so there is a small amount of height that the ball has to begin with. The ball does not have 0 gravitational potential energy. And again, that goes all the way back to our whole discussion about how, these rotational ones can be harder because you have to do it from the center of mass. And so that's why we had a torque that was only L over 2. And that's also why here when it excuse me, when it swung down, it only swung down by L over 2. Anyways, I'm putting a lot of words here because I have a strong feeling that this one, initial height, could have been overlooked. Now, another thing that could also be overlooked is when we're talking about its initial kinetic energy, not only is the object translating, but it is also rotating. And so we have an initial kinetic energy and an initial rotational kinetic energy. Now, the other end of the story is kind of nice because it'll roll up and come to a stop. And again, we're going to measure from its center of mass here to this height. Yeah, because it's did they say center? Yeah, see, I want to emphasize here. It's from the bottom of the ramp does the ball center roll up. Now, the center of the ball is the center of mass. So this side's much easier to deal with this than this side. I guess we could have done, well, there's a lot we could have done here, but I think this is the natural way. But my point is this would be then an MGH because it's come to a stop, so it only has gravitational potential energy and no translation or rotational kinetic energy. And now we can begin to simplify things. Maybe my first step is to do the harder rotational stuff because now we're back to a solid rubber ball, and so it's that same table that we needed twice already for our rotational kinematics. It's that 2/5 mr squared. And the angular speed is v over r, and so when we square it, we get v squared over r, and that equals to an mgh. And I think we could probably, like some of these other ones, just put some numbers in, and every term is kind of known. But in this case, I kind of like to just simplify things and get rid of the m's. Oh, actually, do we know this? Ah, no, I guess we have to do that. They don't tell us. And so unlike the rod ones on the easier multiple choice, we must cancel off the m's. Otherwise, we'll get stuck. Now, here we can cancel the r's. So we don't really even need the r or the omega here. But we could have calculated the omega, and we're given the r. Although we'll still need the r for this piece of the puzzle. So we're going to need it. I guess there's also a 2 canceling off here. Oh, and then might be kind of nice just to divide everything by g so that they cancel here, and then we have an r plus. And so you have a 1/2 v squared over g from this term, and this is a 1/5 v squared over g, and of course that equals RH. And I guess I kind of like it in this form because now I can see that how high it goes is because of this piece, which is the energy of translation. That's kind of the first thing you learned in this class. And now the next thing you learned was that it would be added energy because of rotation. So there's an added energy due to the rotation of the wheels. There's also, for that matter, an added height just because of the physical dimensions and the center of mass. And so that's these two that you might skip over. Hopefully not this one. This one might be a little bit more obvious. But anyways, let me put this in. So that's a 0.1. This right here, let's go to our V. What was the V in this problem? 4 meters. So this should be 4 squared, which I'll just put that as 16. Divide by 2 and also divide by 9.8. And so that's a 0.816. So that's how high it goes based upon translational kinetic energy. This one here, 16 divided by 9.8 divided by 5 is 0.326. So that's how much height you would get from its rotational energy. In fact, if I add these two, let's see, 6 and 6 makes a 12, carry a 1, that would be a 2, 3, a 4, and that'd be an 11. Okay. So if you only did the energies, and you did both of them, you'd get 1.14. I'll just drop that one for significant figures. But above the ramp gives me 1.24 equals H. So there, that last little piece could be easily overlooked. But it's got that whole concept of where do you measure the energy from the center of mass, and that's a big one. If you got that one, good. Congratulate yourself. All right, so one more free response, and we'll be done. Oh, and I've been talking way too much. I like to keep it under an hour, but we've had some good educational stuff going here. All right, so let's see. And then this is our fluid one and our fluid statics. We're going to get into fluid dynamics after this exam. I guess that's today's lesson. So hopefully you're learning that now that you finished up the exam. But it says here, water has a density of, and hopefully you know that. And then we have some other object that has this density of 0.7. And if you float the object in water, what fraction of the volume will be above the water? So this is kind of like that last multiple choice one, where we're thinking about putting an object, and the last multiple choice had a boat that we could put in salt water or we can put in fresh water. This one we're definitely putting into fresh water. But if you remember the discussion on that one, we said, look, what's pulling it down is mg, and what's lifting it up is the buoyant force. And they have to match. And so maybe the first thing to say is the buoyant force equals the weight of the object. Now, here's where we could do a couple of steps. This mass is the mass of the object. So let me put OB for object. And here's why I say that. Because the buoyant force is Archimedes' principle. Archimedes' principle says that the upward buoyant force is equal to the weight of the fluid displaced. So I'm going to put an mg again, but this time I'm going to put DIS for the fluid being displaced. Otherwise, it might look like these are the same thing. Now, the g's cancel off, but what it's saying here is the mass of the object and the mass of the fluid displaced are the same. And again, that's back to that 50-ton ship one. We can see that they're, if you have 50-ton ship, you're going to displace 50 tons of either salt water or fresh water. And they're different volumes, but they're the same mass or same weight. Okay, but sorry, I got sidetracked on that boat problem again. But this is a lot like that. We just don't even know what the mass of the object is. So we need to make another statement because we know density is mass over volume. So we can replace mass with density times volume. And we can do the same thing on the other side. However, let's be careful here. This would be the density of the object, and this would be the volume of the object. Whereas over here, this is the density of what's being displaced. That's the fluid. So maybe I'll put an FL, and I'll put volume displaced. Because we do know the density of the fluid. That's a 1. And we also know the density of the object. And again, it might look like we're kind of stuck, but the question wasn't really asking about the weight or the volume of the object or of the fluid displaced, but it was really asking about a fraction that is above the water. And here's how that works, is if we come over here and say, okay, what about this ratio of the volume displaced over volume of object, which mathematically would be 0.78. What does that really mean? And coming back to our picture, you're saying what volume is under the water, that's the displaced, compared to the whole thing. So this is really a fraction under water. And so 1 minus that fraction would be above the water, which would be 0.2, or I would write it as 22%. So 22% of this object should be floating above the water, and 78 should be below the water. Okay, well, I hope you did well on it, and I'll sign out. Take care now.